Hi everyone, first video in the Polymers series. Lovely image there of some polymers on a beach. So I don't think I need to talk too much about that, but we're going to talk, I think we talked about it last one, about polymer waste. Okay, our inquiry questions. What are the properties and uses of polymers? So we're going to look at what polymers are, and we're going to look at some particular examples from the syllabus. And we need to know their properties and their uses, and also I would like to add to this question their structure. It seems you'll be assessed on structure, properties, use. So I've kind of tried to keep it simple. Alright, there's the syllabus points, a little bit of context here. So the 20th century could be called the plastic century. So knowledge of and the manufacturing of plastics has increased exponentially over the 20th century into this century. So we've now found ourselves in a new century with the habit of single-use plastics, and as well as ecosystems inundated with plastic wastes, and both the small plastic and the large plastic, the macroscopic and the microscopic. So the macroscopic, big chunks there, fragments, definite problems with that. And then you've got this really small microscopic or microplastics, separate problem, very different problems with both of them. Okay, so polymers, very long chain organic molecules that contain repeating units, long chains. So they're made from the reaction between smaller units to create an immensely long repeating, or a macromolecule, a very large long molecule, long chains. Look at this picture I've got here. It's a long alkane. Okay, so the smaller units that react with each other are called monomers, and monomers reacting together to make polymers. Okay, they're present in nature, and also humans have learnt the chemistry to make different ones that are not found in nature, or we can make in labs the ones that are found in nature as well. So just a brief slide on that. Natural versus synthetic. A natural polymer can be said made by biological processes. So examples of natural polymers are silk, wool, hair, starch, cellulose, and the most important, DNA. And a synthetic polymer, we might use the term for the ones that do not occur in biological processes that humans have made. So like polyethylene and polystyrene. And so the line, there's a bit of a grey area between the two. Okay, so we as humans now can manufacture DNA, and we can manufacture cellulose, and we can manufacture those natural polymers. And we can also, I like this one as well, we can also alter the DNA so that they can produce, we can alter the DNA of bacteria so they can produce synthetic polymers, or naturally, the bacteria makes them, but we change the nature to make what we want. And we could call those as synthetic. So there's a grey area. Okay. One thing to say, being pedantic, not all polymers are plastics. A plastic is a term that's older than what muggles call plastic. It means pliable and malleable with heat. Okay, so the term plastic was around before polymers. It was a general term before that for anything pliable and malleable with heat. So synthetic polymers that are pliable and malleable with heat are called thermoplastic polymers. And there are many synthetic polymers that are not plastic and are called thermosetting polymers. So here under the polymers, you've got thermosets. They can be melted. Oh, sorry, thermoset. Set being the word that they set. They cannot be melted. And you've got thermoplastics, which can be melted. Okay, so technically we should be using the term plastics just for the ones that can be melted and reformed. And the thermosettings are the ones that cannot be melted. I'll talk more about their properties in a minute, but we tend to just use plastic and polymers for the whole lot, okay? So, thermoplastics, they soften when heating, or pressure is applied, and they can be reshaped. And so these are the plastics that are easier to recycle. Okay, they just need to be reheated so that they melt, and then they can be reformed. So common thermoplastics are polyethylene or polyethylene, polyvinyl chloride, PVC, and polyethylene terephthalate, PET. You've heard that term before. Okay, the ability to melt and reform is due to not having any or many covalent bonding between polymer strands. So you have polymer strands, and they have dispersion forces next to them, and they might have dipole-dipole, but there's no covalent bonding between strands. And we'll talk about those other plastics more. Those GIFs don't turn out on PDFs, do they? Anyway, so thermosetting polymers do not melt when heated. What they do is just combust. And this lovely GIF, if it was working here, you'd just see it. You know those plastics when you put heat on them, they just burn. They don't melt. They just combust, and they give off fumes and stuff. Okay. So, very hard to recycle because you can't reheat them to remold them because they just burn. They have covalent bonds between their strands, and that's why they can't be melted. A lot stronger between the strands. So they're more stronger than plastics, and more durable, and more chemical resistant. And these properties come down to these bonds within the strands. So common thermosetting polymers are polyurethane. You'll often encounter those as insulating foams. Melamine, so the worktop surfaces, you want them to be resistant to heat and chemicals. And also the plastic called Bakelite, one of the oldest plastics that humans have made. And they're used for resistors, and if you've been in the old houses, you might see them as those classically brown or black switches. They're really, really chunky switches, or old telephones, that black or brown, really thick plastic. That's called Bakelite. One of the first synthetic plastics to be made. Okay, we talked about the use of ethene in the last couple of chapters. And remember, it is obtained from crude oil. It's actually found a little bit in there. Or the cracking of crude oil fractions. So long chain alkanes are undergoing a reaction to break them into smaller parts. And one of the ones that we do really want is this molecule here, ethene. 2 carbons with a double bond in between. And then the 4 hydrogens. Okay. It is widely used as a starting material for polymers. Very, very handy. By itself, it will polymerize with itself to form polyethylene, because ethylene was the old name for ethene. It can also undergo reactions itself before polymerization to make different polymers. So we're going to talk about the reactions. You can react ethene to give it different do like substitution reactions, and then polymerize it, and you get a different plastic. So, one note here, the polymer industry and naming system still carries forward older naming styles, like how I was talking about polyethylene. So pre the IUPAC, the International Union for and Applied Chemistry, forget what the P stands for, ethene is still widely called ethylene in the industry, and so you'll need to recognize that term, okay? And it's in the next syllabus point too, so it's important that you recognize that ethylene is ethene. All right, syllabus point. Model and compare the structure, properties, and uses of addition polymers of ethylene and related monomers. For example, blah, 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 blah. We've got 4 examples, okay? So we need the structure, properties, and use of a certain type of polymer called polymerization reaction, called addition polymerization. So we're going to look at addition polymerization, and then we're going to look at the polymerization of ethene or ethylene, And then we could look at these examples of these different ones. Okay, so addition polymerization involves, you need monomers that are unsaturated. They must have a double or triple bond in them. They could have a double or triple bond. And so these monomers are going to react together and they lose 1 degree of unsaturation to form new interlinking bonds. Okay, it is an ongoing addition reaction. Okay, it's an addition reaction ongoing between many of these molecules. So for example here, I've got all these ethenes lined up, and what happens is 2 of the electrons that are in the double bond come out and form a new bond in between 2 of the monomers, and they reform and they put a new bond in between them. Okay, so you're getting rid of that one and you're forming a new bond in between, and it's ongoing. So you form a chain, an alkane chain. Okay, so ethene will react with itself to form a single long alkane chain, and the addition across the double bond is the electrons that were in the double bond are now in new covalent bonds between the monomers. So addition polymerization involves a double or triple bond, and those electrons now forming a new covalent bond between 2 adjacent monomers. Okay, here, because we're going to contrast it with another type of polymerization, there is nothing left over. Okay, all of the atoms that were here at the beginning are there at the end in that long chain. Okay, we've added across the double bond, so there's no byproduct. What we do is we just get the long chain polymer. Okay, so PE, polyethylene or polyethylene, notice the polyethylene is still sticking to the old name. So the monomer for polyethylene, the recognized name ethene, the old name is ethylene. There's the structure there. 2 carbons, double bond between them, and then the 4 hydrogens. When that polymerizes, words, you form, the correct name is polyethylene. I know that's annoying. I would prefer to call it polyethylene, but the IUPAC wizards, as I call them, have said, no, we're going to call it polyethylene. Okay, so what ends up forming is an ongoing alkane chain, fully saturated, carbon-to-carbon single bonds, and the 4 hydrogens. And notice here this new notation, there's these big square brackets around it and this N underneath. Just like the N in maths, it means it's ongoing to any number. Okay, so these chains can be tens of thousands of these units long. So what we do is we tend to put brackets around the base unit, and it started with ethene, so it's 2, and then we put the square brackets around them and a little subscript N after it. So polyethylene can be used for a variety of properties, can have a variety of properties depending on the conditions of the reaction, and we're going to learn about some of the conditions soon. There's 2 main types of polyethylene. There is low density polyethylene, abbreviated to LDPE, and also high density polyethylene, HDPE. I'm sure you've seen them on bottles if you're at all curious. You see them recycling symbols. LDPE in general is flexible and soft. High density polyethylene is less flexible and has a higher strength. Okay, the main uses of polyethylene. So they can range from soft flexible films all the way up to hard rigid products. Low density is used to make plastic bags and cling film, that really thin flexible stuff, flexible bottles like squeeze bottles, and tubing that's flexible, and also the coating on milk and juice cartons. You know those Tetra Paks? They're coated in low density polyethylene. High density polyethylene is used for rope, rigid piping, outdoor furniture, crates, milk bottles, jerry cans, and other containers for chemicals. I'm sure you can imagine all of those and know the properties of them. Okay, we need to go into a bit more depth on how on the polymerization reaction of polyethylene. So, during the polymerization process, to make both types of polyethylene, low density and high density, a free radical initiator, remember what a free radical is? It's something that has an unpaired, unbonded electron. Very reactive. And it's used to start the reaction, the polymerization reaction. This initiator will break the double bond of an ethene and leave the ethene with a free radical. So the free radical initiator breaks the bond, makes whatever's left over into a radical, and then that keeps on reacting away. Okay, and what ends up happening is you get a chain. So the initiation step, there's our ethene and there's our initiator. Now you don't need to remember that it's a peroxide one, hydrogen peroxide that we've got here, but just remember a radical initiator. What ends up happening is it reacts and you get some other stuff, but you break the double bond in the ethene and you get a single bond with this radical on the end. So we've initiated the reaction, we've got a very reactive thing. What happens then? We get the reaction propagating, we get it building, we get our product building. So we have our radical there, and it comes across another ethene. And what ends up happening is you get bonding across it, and the radical is still there, okay? And notice here it's on the end. We'll talk about that more. And that keeps on going, and that repeats and repeats and repeats and repeats and repeats. And that's why I'm drawing a squiggle there. Repeats until you've got chains tens of units long. And what can happen is, after a certain amount of time, the concentration of ethene will go down and down and down and down. When you've got a more and more longer chain, concentration of that will go down, and so then there will be eventually a significant concentration of these radicals left over, and one of them is likely to meet each other. When the two radicals meet, they join across and they form a I'm going to say a neutral molecule, but that's just charge. But well, the two lone pairs electrons come in and form a new single bond, no more radical, and you've got this bond in between. So two unpaired electrons into there, forming a covalent bond, single covalent bond with two electrons. And that's the termination. That's how the reaction ends. Okay, so at the beginning, you don't have many radicals, but you have a lot of the ethene. They keep on making longer chains until the concentration of your ethene is way down, and you've got a significant enough concentration of the radicals that they meet and they stop the reaction. Okay, a bit more detail on the process to make high density PE. The pressure we class as low. It's usually less than 5 atmospheres. So we don't need significant infrastructure to make that. We just need a good strong tank. And temperature we also class as low as well. It's only about 60 degrees Celsius. And we need a catalyst to make high density polyethylene. And what this catalyst does, there's a weird name for it after two people who found this catalyst, Ziegler-Natta. What this catalyst does though, if you don't want to remember the name, remember what it does. For high density polyethylene, we use this catalyst, and this catalyst makes sure that the radical is always on the end of the strand. Okay, like I've got up here, the radical had to be on the end of the strand when there was only two, but here the radical is on the end. And the catalyst will also come along and make sure that no matter how long this chain is, that radical point will always be on the end of the chain. And so any new monomers joining will be on the chain, just making it longer and longer and longer, single strand. Okay, that's what the catalyst does. It also makes that the reaction reach equilibrium quicker. So it increases the rate of it, but that's about it. So, as I just said, because of that, it ensures the radical sites are on the end of the chain. The process forms unbranched linear polymer chains. And because they're unbranched and linear, they can pack together in a close way, okay? Adjacent strands can move close to each other, okay? The dispersion forces, because they can move closer to each other, are higher, okay? because they're reliant on distance. The closer they are, the higher the dispersion forces. And that leads, well, I'm comparing that to low density. The branches can get closer. So I'm getting distracted. We'll contrast that later to low density. But anyway, those linear strands ensure that they can get close to each other. So therefore high density. Okay. Higher melting point, it takes more energy to pull those strands apart. Less flexibility, they hold on to each other strongly. And a slightly higher density. The density for higher density, even though it's called high density, is just under the density of water there, 0.95 grams per cubic centimeter. Okay, so linear polymers, like I've got down here, these long chains that are close to each other, and they can approach closely. So it allows the dispersion forces between the two strands to be quite strong because they're quite close. So even though they're alkanes, they are long enough that the dispersion forces are so hard to overcome that at standard temperature and pressure, these things are solid. So think of just taking one of those carbons and having methane, two methane molecules, not much attraction, not much dispersion forces at all, and they're a gas at standard temperature and pressure. Once we get along to like pentane and hexane, they're strong enough and long enough that those dispersion forces are stronger that they can hold it into being a liquid. But here we've got such long strands and such higher dispersion forces, even though it's the weakest intermolecular force, it's still strong enough over those large tens of thousands of units long to make them into solids. And that's pretty cool to think about. Oh, one other property is, because they can get so close, other molecules can't really get in between. And so that is also the chemical resistance. Okay? Let's contrast this to low density polyethylene. Okay, our pressure here is high. We're talking thousands of atmospheres. Large big tanks with lots of reinforcing, lots of safety monitoring happening there with low density polyethylene. Okay, we've got a higher temperature, 300 degrees Celsius, and look, no catalyst is used. Okay, so no catalyst, so the site of the radical is not always going to be on the end of the chain. It could be anywhere in the chain. And what that means is you're going to build, not from the end of the chain, could be, probability-wise, a little bit, but more than likely in the middle of the chain. And what ends up happening is, as propagation occurs at any site along the chain, you get a branching polymer. You get a polymer that may have a main chain, but you're getting branches off there, okay? And so these branches, when we're talking about consecutive chains, two branching chains trying to come together find it hard to do so because of all the branches. Think of two large tree branches. If they were on the floor, don't rip them off a tree, and try to bring them close to each other. The main branches, they can't get close to each other because all the little twigs, all the little side branches are preventing them. That's what happens with low density polyethylene. And so you get these larger kind of gaps in between the consecutive branches, and so it's slightly low density. And it gives it different properties. Okay, the dispersion forces between the two branch chains are low because of the increased distance away from each other. Okay, compare it to the straight chain ones in high density, they were quite high because they can get close. Okay, so because they can't get as close, they have a lower melting point and they have a lower density. Notice it's not too much though, it's only 0.9 grams per centimeter cubed. There's not much density difference there, but there's enough in the properties of the material. It's also highly flexible, okay, because it's not got those large dispersion forces holding it together. So for LDPE, there's no catalyst to ensure that the end of the radical site is on the chain. So since any carbon can be a radical site, the propagation occurs anywhere. So here I've used the same kind of thing that I've used earlier. We've got our initiator, it puts the radical on the end because that's the only choice. But when we've got that reacting more, we can end up with a radical site halfway along the chain, not on the end. And because of that, what we have is you're going to get a branching polymer. Okay, do you like my copy paste here? So I've got branching polymers. Try to demonstrate they can't get as close to each other. There's these large gaps in between. And because of these gaps, the dispersion forces are lower because you can only get certain sections close to other sections. Certain attractions there, but not as strong as high density polyethylene. So this means weaker dispersion forces and a more flexible low strength polymer. It is not chemical resistance, as other chemicals can fit in between here. You can suddenly get something in here that might react and break it apart. Okay? So not as chemical resistance. So in these diagrams, you've got those squeezy bottle kind of things happening. And you've got Glad wrap or cling film there. You've got these bags here. You've got the coating. Didn't I say that? Well, you got the coating on the outside of the cartons, the squeezy bottle for honey and stuff like that. Okay, here's a table that goes through and summarizes what I've just been talking about. I'm not going to take some time to do it. Just a nice summary comparison chart. Good to have kind of in your head, knowing the generalizations going into the HSC. So here I've just done a couple of models using polymers, using my daughter's Duplo. I like these. So low density polymerization, you've got one monomer unit, okay, ethene. And the polymerase, so you get the initiator going in, so propagation can happen, but the addition site can happen anywhere on the chain. So we've put one on the end, but we've also put one up here. And polymerization proceeds, so we're getting some building, but we're getting some branching, okay? And as it goes along, you're getting more branching, and you're getting a chain with branches. Okay, let's contrast this with high density. Monomer, another one, because the radical site is always on the end, okay, you get a long line of these, a straight chain one, because the radical site is always on the end. Okay, so you get a linear high HDPE chain. Okay, and now let's contrast how they line up together. On the left, we've got our low density. All these branching between successive chains, they can't get really close to each other. Low dispersion forces. Successive chains of high density, they can move really close to each other. Dispersion forces are stronger because there's a shorter distance between the two. Only tiny distances. Okay, let's finish up with 2 past HSC questions. So this one's from 2001, question 1. Ethene may be converted into polyethylene or polyethylene. What type of reaction is this? Well, we haven't learnt about condensation reactions yet. We've learned about hydrolysis. Remember, hydrolysis was when you have a double bond and you're adding water and you're producing an alcohol and a hydrogen across there. So it's not an oxidation, it's a polymerization. Nice first question to really get you into a new HSC, into your exam and go, something making into poly something? That must be polymerization. Okay. So this one's also question 2 from 2012. So very early on in that HSC as well. So easier questions in the multiple choices early on. They in general get harder as they go along. Not linearly, but anyway. Which of the following compounds represents the X in the flowchart? So what do we got here? We've got C2H4. That fits the CnH2n. Oh, there must be 2. That must be ethene. That's the only thing it could be. Okay, something happens to ethene and then it makes a polymer. Okay. Which of the following compounds represents X? Okay. Oh, I should have put this question later. I put this too early. I should put that after this one. We'll come back to this one. I've just put it in the wrong spot. Anyway, what a good space to end the video on a mistake. Good job. Okay, I'm going to stop it there. Next time I'm going to look at how we can adjust ethene to make several different other polymers that are on that syllabus point. Thanks for your time.